Recording. Excellent. Okay, how we're doing? Oh, the enthusiasm. Yeah, happy ICML deadline to all who celebrate. Right, so let's see here. In terms of announcements and boring stuff to start the lecture, just a reminder that you should do your homework. At this point, hopefully we've all downloaded and tried the starter code for the assignment. If not, you're officially behind. And other than that, once you start it, I'm sure you won't be able to sleep until you finish. So I look forward to seeing all your interesting homework solutions. Beyond that, we actually managed to post the weekly quiz on time this time, so you got plenty of time to do it. As a warning, I wrote some of the questions, and so Chris tells me they're harder than they were before, but mildly. Sorry, but they are conceptual, so like there's not like you need a whole lot of time to answer. Just think it through. The good news is we dropped them, and they're a small part of your grade anyway. Any questions, concerns, comments? Favorite recipes? Interesting vacation destinations? Killing me. Detroit, yeah, that is the city. Yeah, fantastic. So let's see here. So today we start the next big chunk of 6S955, which is eigenvectors and eigenvalues. This is like one of the sort of pillars of linear algebra and numerical linear algebra. And it's also our first encounter with algorithms that are one of the main classes of techniques in numerical methods, namely iterative techniques rather than things that kind of function in closed form, right? So far, when we did Gaussian elimination, LU factorization, Cholesky, and QR, all of those like looked like algorithms in the conventional sense that we're used to from like 6006 or whatever class you've taken from undergrad algorithms, right? Like, for instance, Gaussian elimination takes n cubed steps. It has a forward pass. It has a backward pass. You know, like all of the, even though it's working with like double precision numbers, like the steps of the algorithm like feel very familiar. For eigenproblems, in fact, one can convince themselves that any such algorithm will not give you eigenvalues if you have exact precision arithmetic. There's a fun algebra argument to convince yourself that this is the case. And for that reason, we're now in the regime of problems that are sort of inherently approximate. Like even if we had a perfect precision floating point system on our computer, so in other words, like, you know, like rather than keeping track of decimal points and mantisses and rounding and all that stuff, we just like, you know, kept the exact value around on our computer, we still wouldn't be able to find eigenvalues in closed forms. There are a lot of different ways to convince yourselves of that. If you have taken an algebra class, then you know that eigenvalue and root finding are like roughly the same for polynomials. And one thing that we know is that like roots of polynomials tend to contain all kinds of weird expressions, which is maybe a good indicator why we can't necessarily encounter an eigenvalue with like an algorithm that terminates in some finite number of steps. So instead, what we do is we successively approximate them better and better and better, right? And this is sort of a bread and butter technique in numerical methods, and it's one that definitely differs from like maybe computer science theory, at least on the very classical side, where you want to like bound the number of steps to get to the exact solution of your problem, right? Here we just can't do that. So the best we can do is sort of trade off between runtime and approximation error. Does that make sense? So eigenvalues are going to be the very first time that we see that, and I think basically the remainder of this course one could basically understand as through that lens, with the possible, yeah, no, I stand by that. I can't think of any other techniques we covered that are really just like finite time nice algorithms. Those are relatively rare in numerical methods. Okay. So that's that. So we're going to spend several lectures on eigenproblems, and then we're going to expand ever so slightly into a different problem called the SVD, which is closely related to eigenvalue problems. As a warning, our SVD chapter is basically newly written relative to what's in the first edition of the book, which means it's likely to contain typos, more typos, I should say. So I encourage you to read it closely and let me know if you find mistakes. But in any event, that'll happen in a few lectures from now. And for now, we're going to stick with just eigenvalue problem. So hopefully we've all encountered what an eigenvalue is in linear algebra class. But I think one thing, especially among our computer science students that I've noticed, is that like you know, when we talk about eigenvalues, like I say eigenvalue, you like if you wake up in the middle of the night and you think of an eigenvalue, you immediately like write down, you know, ax equals lambda x, and that's great. But I think there's a totally reasonable question that one should ask when you take a linear algebra class, which is why the heck would I want to solve this problem? And I think sometimes that piece kind of gets lost or elided a little bit, and then you kind of fill it in later, right? Like you take undergrad linear algebra, you learn what an eigenvalue is, and that it's sort of an object that you can compute, and then like suddenly you start noticing in your future classes that it's like a helpful object, and it's just totally the wrong way to teach this stuff, in my opinion. So in any event, you know, to get off of my soapbox here, we're going to spend a little bit of time at the beginning of today's lecture just kind of, I want to give you all an intuition for like, when I see a problem out there in the real world, you know, your job is going to be to recognize it as an eigenvalue problem or a linear problem or positive definite matrix or whatever. Like, how can you eyeball a problem and know that secretly it's an eigenvalue problem? And, you know, there are like millions and millions of different ways to see that. And from my perspective, there's sort of two very principal ones that often come up. One is, you know, you're given a symmetric matrix, optionally positive definite, and you want like a convenient basis that somehow is related to that matrix. And the other one is with a very specific optimization problem that we'll see later on. Okay, so we're going to do a couple examples of that, and then our goal for today is to do some of that and to review some eigenvalue theory, which is going to be relevant to the algorithms that we'll derive in our next lecture. Okay, that's going to be our basic plan of attack. So we're going to start with motivating eigenvalue problems, and then the next lecture we'll come up with the basic algorithms for eigenvalues. The lecture after that, we're going to do algorithms that try to find more than one eigenvalue at a time, and then eventually extend to the SVD, which is sort of an application of all this stuff. Okay, so let's start from an applied perspective, and in particular, we're going to motivate a tool that I'm guessing many of you have used in your everyday lives, which is something called principal component analysis. Now, which I think is a sort of basic application to eigenvalues, and to me, one of the sort of simplest ones to motivate why you might want this stuff. Okay? So let's say that we go out there and we collect a bunch of data points, xi, they're in some Euclidean space, and they contain all kinds of numbers in them, and they're on different units, right? Like age, weight, blood pressure, heart rate, I don't know, favorite color expressed in a wavelength. So we should stick in numerical form for today. And at the end of the day, we're trying to find correlations between different dimensions. You know, like as you get older, you tend to like the color green, something like that. One might ask why, and I don't know. I have to think about that one. But I have found myself like gravitating toward green recently, which I can only assume is correlated with approaching 40. In any event, let's say that I want to take my data set. And now my goal is to take my data and sort of compress it. Right? So in other words, for example, let's say that like your weight is always 2 times your age, which would be maybe the case in stone. But in any event, in that case, did I really need 2 different coordinates for my data? No, right? Like it would be perfectly fine to just know your age, and then you can predict weight from that, right? And so more generically speaking, let's say that we think secretly out there, we're going to stick to just 1D for now, that there's some one-dimensional subspace, some vector v, where I think that all of my data is roughly a different multiple of v. Does that make sense? Right, this would be the case if like your age, your weight, your blood pressure, whatever, were all multiples of one another. Now in reality, of course, that's not true. For most of us, I'm sure there's like one lucky person out there in the universe. But in any event, for the rest, but this is some model to begin to try and explain your data. Now, first of all, in this model, does it matter the length of v? In some sense, not really, right? Because what I'm really looking for, you know, so if I've got my data, maybe it's 2-dimensional, like that. It's like very hard to draw a biased data set that has the bias that you want to happen in a particular model. You know, so our job here is to find some v that kind of points along my data like that. And if I scale it, that's still defining kind of the same line through my data points, right? Because at the end of the day, v is getting scaled by some constant c, right? So if I choose a different scaling of v, then I just have to scale c up or down to respond to that. Does that make sense? So at the end of the day, it's perfectly fine to say that I want all of my data points xi to approximate some constant v or c multiplied by a vector v, where v has unit length. right? So essentially, I'm just going to constrain the length of this vector to be 1. Yeah? And all that does is kind of put a scale on the constant c. Okay. So incidentally, have I removed all the ambiguity in my problem? Thank you, TA. We know our vector up to sign here, right? So we still have v versus minus v, and one thing you might recall from eigenvector problem is that there's also an ambiguity in that universe, so you can kind of see where we're headed. Okay. So I think one thing to realize, like, I think oftentimes because we like learn about eigenvectors and then we learn about optimization, we oftentimes say like, aha, like, so how would I model this? This is with an eigenvector problem. The question you really should ask is like, well, what would be the most obvious optimization problem, and does it happen to fit into this nice formalism we have? And of course the answer is yes, but it's not obvious. So in particular, if you asked me to go out and model this one-dimensional problem, I think I would come up with something like what I've written on the screen here. So here, v is an unknown vector, right? And what I'm saying is that I would like to find a vector v so that it's the projection of each data point xi onto v is relatively close. Do you see that? Like, that's essentially the objective function here. And then just to kill the ambiguity, and maybe also to avoid the v equals 0 degeneracy, I add a constraint that it's unit length. Any questions about this formulation? Like, I think this is just a direct translation of this picture that I've drawn for you onto mathematical kind of optimization terminology. Yes? So the dimension of v is the same as x, right? Because it's got to be, otherwise projection doesn't really make sense. But we can sort of call this one-dimensional principal component analysis. Like I'm not looking for more than one v that makes a plane. For now, we'll come back to that later. Yeah. Does that make sense? So I don't know. I guess to me, like if I were to explain PCA, I would start with this equation. But from this equation, it's not actually obvious that this is an eigenvalue problem, at least to me. At least to me as the person that's speaking to the room full of grad students. But to me as a numerical analyst, of course, this is an eigenvalue problem, and what we need to do is show it, right? So essentially, oh right, oops, and my slide asked what does the constraint do, and spoiler alert, we already answered that. Sorry. So here's our picture, right? So again, we're looking for a v that points along our data, and then this x minus the projection onto v are like the little residual vectors. And notice we actually proved in the last lecture that the residual vectors, like these little lines here, should be perpendicular to the axis that we derived. Of course, in 2 dimensions, this is kind of the only picture we can draw. But in higher dimension, it's a little more interesting. Okay. So v is unit length. And so in particular, right, when we project x onto v, we're trying to look for c. So just as a bit of review, what is ci? In other words, what's the length of the projection of xi onto v? Remember the formula? Thank you. See, they tell me I gotta wait. If I wait long enough, somebody will feel the pain. Okay, good. Yeah, that's right. So obviously, if I want to project a point xi onto a vector v, I just take the dot product because v is unit length. Yeah, that's all. So we don't ask tricky things here. Okay. So in particular, remember our objective function. It was the sum over data points I of xi minus the projection onto v hat of xi, right? That's the length of the residual squared. And now, thanks to our colleague who finally put the rest of you out of our misery, we know that this expression is the sum over I, xi minus xi dot v hat xi. Like that. Does everybody agree? Some kind of acknowledgement. People, you're killing me. Yeah, look up, nod. Like a thumbs up, maybe. There we go. Thank you. See, 2 thumbs up, which is good, because Paul's still looking down. Okay, so, right. So we've got this expression here. Essentially, if we look at the board, whenever we have an expression like this with a big square on it, like this is screaming out for us to expand the square. We can't help ourselves but to do that. So let's write that expression. So we have that this is equal to the sum over I of a bunch of stuff. So we've got xi squared like that. Now we've got the cross term. So what is that going to be? We've got a 2, let's see here. We've got xi dot v times xi squared, like that, plus, wait a second. Oh, I'm sorry. See, you guys are so agreeable. Even when I write completely wrong stuff on the board, you just sit there and you wait for me to notice that I made a mistake. This should be v. There's something about this like lecture style that I think just lulls everybody into this false sense of complacency. But remember that the projection onto v is a multiple of v, not x. Yeah? You guys understanding it all, or are you just like totally brain dead? You just like rolled into this room and now you're passed out? Yeah, I don't want to know the answer to that. Okay, so in particular, the cross term should be that, right? Because we've got xi dot v, xi dot v. Okay? And then plus, we've got xi dot v squared, and then what is v hat dot product with v hat? 1, thank you. That's right. So this is our expression. Okay? But notice that these are actually the same. Isn't that convenient? So in particular, this thing is really the sum over I of the norm xi squared minus xi dot v squared. Cool? Now remember the unknown in our problem is what? It's v. Yeah? So what does this thing contribute anything to our optimization problem? No, right? So really, what is this thing? It's just some constant with respect to our unknown minus the sum over I xi dot v quantity squared. Okay. So let's say that we're going to define a new matrix X whose columns are the xi's. So this is like x1, x2, and so on like that. Hopefully now you guys are kind of getting used to that convention from your homework. So like we're just going to take our whole data set and put it into a matrix whose columns are the data points. Then one thing you can notice is that if I do x transpose times v, what is that going to be? It's going to be a vector where I take x, I flip it on its side, now I take the dot product with each of the v. So this is like x1 dot v, x2 dot v, and so on. Does that make sense? Hopefully we're getting used to this little trick. This is like a usual thing. It's also a good way to speed up your code, right? Like it's usually better to work with these kinds of expressions than to like have a bunch of for loops. Okay, so in particular, that indicates to us that this is really a constant minus the norm of big X transpose times V squared, like that. That make sense? By the way, in statistics, what do they always talk about? You can maximize variance and minimize. What's the other side of that theorem? Like minimize the residual and maximize variance, and those are the same thing. Notice that's basically what we proved here, just in linear algebra language instead of like expectations. Okay, right, and of course, this expression here is the same as V transpose X, X transpose V, like that. Whew. All right, everybody with me so far? Fantastic. Okay, so what is our optimization problem then? Well, essentially what we've shown is that that is equivalent to this problem on the board here. Right? That's what our little proof has shown. That we can understand this problem as maximizing over V the norm of X transpose V squared, subject to the constraint that the norm of V is equal to 1. Okay? Right, notice I had to swap min and max here because there's a minus there. Okay. So basically, anytime that we see a quadratic function with a single quadratic constraint, this is starting to scream out that we have an eigenvalue problem. Right? This is one of the patterns that I want you guys to be able to pattern match. Like quadratic thing with like a constraint, which is the norm equals 1, leads to an eigenvalue problem. In my mind, that's like one of the prototypical ways that we get eigenvalue problems. And so in particular, let's actually do it just once as a reminder. So let's write down the Lagrangian of this thing. So remember, Lagrangian is a function of the unknown x and a Lagrange multiplier, lambda. This is everybody's least favorite little calculation. And so we've got the objective function here. In fact, just for fun, I'm going to put a 1/2 there. Right, constants don't really matter in these objective functions, but it does make our algebra a little nicer. So our Lagrangian is going to be 1/2 v transpose x transpose v, and then we've got plus lambda times 1 minus the constraint, like that. Incidentally, by the way, we can do the same thing with the constraint if we want, right? Like when 1/2 the norm of v is equal to 1/2. But by the way, none of this matters. All I'm doing is just anticipating that I'm going to get rid of some constants by doing this. That's all. If you didn't, you would just do it after the fact. Okay. So what are we to do? Well, remember how Lagrange multipliers work. You set up your Lagrangian for your constraint problem, which is basically the functional plus lambda times the constraint, right? And then you just set the derivative of this thing equal to 0 with respect to x and lambda, right? We know the derivative with respect to lambda is just the constraint. The derivative with respect to x is the interesting one. So in particular, we have 0 is the gradient with respect to, oh no, I'm sorry. I keep doing the same thing. This is a function of v, right? V is our unknown. Have I lost you guys? This is the kind of thing that loses people. You should tell me. It's okay. All right. So we take the derivative with respect to v of our Lagrangian like that. Now, hopefully in this class, we've gotten far enough along that we can start to pattern match because we've done basically this proof 6 times now. What is the gradient of this expression with respect to v? Yeah, I heard 2xx transpose v is what I hope that I heard from you. And of course, the 2 and the 1/2 cancel here. So we have x transpose v, like that. This doesn't have a derivative with respect to v. What is the derivative of the norm with respect to v squared? 2v, which is canceled with that 1/2. We have lambda v. Now you can see why I chose to put all those 1/2 where I did. Everybody with me so far? So in particular, we have x transpose v equals lambda v. So what have we shown so far? We've shown that v is an eigenvector. We have to be a little careful because I think at this point, sometimes we jump to like the biggest or the smallest eigenvector. We haven't actually shown that yet. Right? So far we've shown that v is an eigenvector of x transpose. Yeah. Which to me, again, is one of the key sources of eigenvector problems, which is essentially minimizing homogeneous quadratic function with homogeneous quadratic constraint. Or I guess inhomogeneous because there's a constant on the right-hand side. Yeah. It means that like I don't have a linear term. Like if I had x transpose v plus like something dot product with v. So then like, right, like another way to think about it, what is the minimum of this expression without the constraint? 0, right? I can just take v equals 0. But I could, like, let's say that, for instance, I added like some other vector w dot v to this expression, right? Then that would no longer be the case. Then this is no longer an eigenvalue problem. Exercise left to the reader is, what is this problem and how would you solve it? And there's some really nice algorithms for that, including one proposed in one of my own research papers. Okay, so, right, so this is what we've shown so far. We have one last homework to figure out, which is which, we kind of know that because we have taken linear algebra that there's usually more than one eigenvector. So we got to figure out which one. So one obvious thing that we can do is just go back to our objective function, right? Like at the end of the day, we're trying to maximize this expression. So we have, again, v transpose x transpose v. And now, what do we know? We know that x transpose v is lambda v, right? So this is lambda v transpose v, right? So, and what is v transpose v? What's that? Axel's got it. A little louder for the people in the back of the room. I know, so you could actually say quieter. It's kind of interesting. Yeah, so this is lambda. That's right. So, what do we know? We now know two things. We know that we want to choose n eigenvector, and that when we do, the objective value is lambda. We're trying to maximize this thing. So when we put all that together, what that says is that the optimal V is the eigenvector of XX transpose with the largest eigenvalue. Does that make sense to everybody? I see some furrowed eyebrows. I'm going to pause for questions. But do you notice that I think that last little step of our proof is one that I think everybody often kind of leaves out. Like you just stop here and you say, aha, it's an eigenvector. But you still have to justify which one. And depending on what problem you started with, it'll change, right? Like for instance, if this were a min, you would have gotten, obviously, the bottom eigenvalue. Yeah. Mm-hmm.
So how would you find all of them?
That's a good question. So like why would you find all of them? I mean, you certainly can. Or we think we can. We haven't come up with those algorithms yet. Yeah, so it's not obvious here. One thing you could do is look at, oh right, so here's our, oops, we want, there's our final thing, and we call that principal component. Okay, so, right, so the question is essentially like, right, so like let's say that I want my PCA space to be two-dimensional, right? Then one thing that you can convince yourself, this is the somebody else theorem that I forget the name, but they're in the textbook, essentially says that if you take the top two eigenvectors of XX transpose, their span is the biggest, is the plane that minimizes the same objective function. It's not obvious from the argument we just did, right? There's actually a false argument that I see in a lot of math classes, which is they do it kind of inductively, like they choose V, and then they say, well, now that I choose V, let's say I want a second axis that's orthogonal to V and maximizes this thing again, right? Then, which is the argument I see all the time. Then you absolutely would get the second largest eigenvector of V. That's quite easy to convince yourself. So in other words, if I said V dot product, I don't know, the first guy is equal to 0, I added that, then you can kind of convince yourself that you get V2. But notice that that does not say that V1 and V2 together span the best two-dimensional space. Right? It's kind of like saying if I have a greedy algorithm, it's optimal, right? So the reality is you actually have to be a little careful. Eckert-Young theorem, that's the name, is what you need to apply here. And we may or may not return to it in this class after we do the SVD. I haven't decided. It depends. One thing you might have noticed is that when I start talking too fast in lecture, then I add theoretical results to lecture to make sure that we don't get ahead of schedule. Yes? Mm-hmm. Yep, this guy. That's right. That's because this isn't linear regression. Ah, yeah. So these are very different models. So in linear regression, right, then you end up with a least squares problem. Right, then you're sort of taking the vertical distance. The difference is that in the PCA problem, you're trying to predict correlations between the different coordinates, right? So a perfectly valid PCA axis points straight up, right? Which is not a function. Whereas in the linear regression case, you were trying to predict y from x. There's like a dependency there, right? So that's sort of the difference statistically speaking. Yeah. I saw your hand and then it went back down. Okay. Any other questions? These are great. I'm glad you guys are thinking. I mean, I think that like many of us, especially because this is a grad level course, have encountered PCA before. But I think this sort of optimization-based argument for like why this is a reasonable thing sometimes gets lost in statistical language. Incidentally, if you go back through the statistics theorems and they show that like you get the best fit sort of maximum likelihood estimate, if you kind of squint to that proof, you'll see it's actually identical to what you did here. Right? You just kind of like, instead of having the sum, you have an expectation. If you don't know what that means, it's fine, because it's out of the scope of our class. Cool. So the reason that we cover that is this is one of our main sources of eigenvalue problem, is that essentially, if we think of like different prototype optimization problems, right? Like for instance, we know the following. So let's say that I have min of 1/2 x transpose A x minus x transpose B. We know that this problem is going to lead us to A x equals B. Right? Like in our little brain translation of optimization problems to numerical tools that we know how to use, right? Now we've just added a new one to our toolbox, which is essentially, if you think about it, 1/2 x transpose AX such that, or subject to, I should be careful, the norm of this equals 1, going to be ax equals lambda x, at least when a is positive semi-definite. Notice that we kind of needed that in this argument, or else this last little piece that we did doesn't work. Yeah. If a is not positive semi-definite, then this is actually still an eigenvector, but it may not be the smallest. It's the one with smallest absolute value. Okay, yes? Is every matrix semi-definite? No, absolutely not. If everything falls apart, then you're solving the wrong problem. Yeah, no, but absolutely no. All matrices are not positive definite. You cannot assume that in this class. A lot of matrices are, and that's a useful property where you can get it. Actually, for eigenvectors, symmetry is enough for a lot of problems. You don't actually need positive definite. But yeah, no. The reason that we see so many positive definite problems is just that least squares problems are intuitive, right? And I think that probably the most common source of positive semi-definite A is when this is really a least squares objective, right? So hopefully, like, the reason I keep repeating this stuff is I want you guys to develop like a code book. I mean, I think that's almost the most useful thing you can get out of a class like this, which is to just recognize in the wild, like, oh no, what have you done? That like, quadratic problems, have a particular structure. This is the kind of solver. This is like why Cholesky really is just solving, least squares, whatever. They all fit together, right? I think it's very easy in linear algebra to like just learn this long list of tools and completely forget that it's actually a very clean story. Okay. So now let's motivate eigenvalues a different way, just for yucks, which is through physics, or more generally through ordinary differential equations. So here's physics. We have F equals ma and springs, and the rest of it is details, as far as I'm concerned. So in general, let's say that I have an unknown vector x as a function of time, and maybe I think of x as like the positions of a bunch of particles all stacked together into one long vector, right? Then, of course, the second derivative of x is nothing more than the forces that act upon x. And a very simple set of forces might be linear in the positions of the different points. Does that make sense? So here's a minor annoyance, which is that this is a second order differential equation, meaning there's two derivatives in time. But here's a cool trick, which is as follows. This, by the way, is a trick we will think about again when we talk about ODE integrators in this course, and we'll see that that's actually maybe not the best idea, practically speaking, but theoretically it's perfectly fine, which is the following. So let's define a new variable. So first of all, one thing that we can do is we can take all of the forces acting on all of the vectors and just stick them in like a, so for example, in 3D space, this would be in R to the 3n, where n is the number of particles. Does that make sense? We're just taking all of our positions and stacking them together. So then we could say that F equal to M, which is really just a diagonal matrix with each of the mass of the particles on the diagonal times this guy, right, which is all the positions. That makes sense? So here's a good trick. Yes?
Just to be clear, the positions here are like vertically stacked also?
That's right. So everything here is in R to the 3n. Right, so notice, by the way, that the forces are linear in terms of the positions, right? It's just some matrix times x. Yeah. Okay. Right. So, yeah. So in this particular case, is equal to a times x, right? Because, like where a is like subtracting positions of particles, right? That's what the Hooke law does. Obviously, there are plenty of nonlinear problems out there in the world. We'll see that when we want to solve a nonlinear ODE, one way to do it is to approximate it with this ODE, and then kind of leverage the fact that we know how to solve this ODE, and then just use numerical stuff to account for the difference. This is a class of integrators called exponential integrators, if you feel like Googling that later. It's one of my favorites, actually. There's a really pretty theory, and nobody ever learns that. I like ODEs. I never get to teach them, but now I do because neural ODE is popular, so when we get to teach this stuff again. Okay, so, right. So one annoyance is this double prime here, but here's a mathematical hack, which is let's define V to be equal to x prime. Okay? Then I'm going to write down a first order ODE, which is the following. D over dt of x comma v. So now, what space is this in? r to the 6n, right? So this is like xyz, 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 xyz. Just tons of coordinates stacked together. Okay? So what is x prime? Well, it's v, right? So in fact, so if this is like that, x prime is equal to v, so I can think of it like that. Does that make sense? This is just an encoding of this expression in this fancy matrix language. And what's v prime? Well, v prime is acceleration, which is m inverse ax, right? So it's sneaky, huh? I love this little trick. So it turns out that basically all ODEs are first order, if you believe in yourself. But the cost that you pay is that this is 2 times the size of the original problem, right? So it is first order, but in a new variable x comma v. That make sense? That's why actually in numerical, like one thing that I think often confuses people is when you crack open textbooks for numerical ODE, they'll have like thousands of pages just on starting first order ODE, and it's kind of like, well, wait a second, like the only ODE anybody cares about is f equals ma, and that's like not included here, but it actually is, just by making the dimensionality larger. Okay, so more generically, I think the basic point here, right, so there's our simplification, is that we often want to solve problems that look like the following. That like you have some unknown vector y, which is a function of time, and it's, so y prime is equal to by, where b is some matrix. Does that make sense? This is a very common ODE to encounter in nature. You see it in power electronics. You see it in physics. I guess that is physics. You see this in physics a lot. And moreover, even if you, what was I going to say? Even if you have a right-hand side for your ODE that's not linear, if you took a Taylor series to the right-hand side, it would be. And then this is a thing you can approximate for a small time. Incidentally, adding a constant shift doesn't really affect this, but I'll let you think it through at home why that's the case. Yeah?
Just to repeat what you said, you said all ODEs, higher order ODEs end up including first order ODEs, you just have to expand the state space.
That's right. So you expand the state space to include like the velocity, the acceleration, how many derivatives you need. It's a good way to put it. By the way, that's why a lot of times physicists talk about phase space. That's like this space. Yeah. And they like that because then you can think of like physics as a bunch of arrows in this abstract space. Okay. So here's the thing. Let's say that I knew all the eigenvectors of B. Moreover, let's say that B has eigenvectors, which is often the case. By the way, like, why should B have eigenvectors? Well, one extremely terrible argument would be that, like, there's something equal and opposite, something. There's definitely some symmetry structure hiding in this matrix B. It's a terrible argument. You should not repeat that in the physics department. Okay. So in particular, let's say that I got a bunch of eigenvectors, yi, with the yi. Sure. So let's say that I have b times yi equal to lambda I yi, like that. And moreover, if I'm so lucky, and we'll actually justify either later today's lecture or in the next one that this is often the case, let's say that y of 0 happens to be writable in the y basis. If you've taken linear algebra, you might remember this thing called the Spectral theorem, which justifies that this is actually a totally reasonable thing to assume. But like, let's say we get so lucky that that the initial conditions for our ODE are writable in terms of only eigenvectors of B, like that. Cool? Well, let's think of, I can actually take y of t, and I can write it in the same basis. So it's ci of t yi, at least assuming the yi span Rn, right? And now I just know that ci of 0 is equal to whatever these given initial conditions are. Now let's start with our ODE. So we have y prime is just equal to the sum of ci prime of t, yi, like that. And we have on the right-hand side, by is equal to the sum ci of t times b times yi, but we know that that's lambda I yi, like that. Does that make sense? So setting these two expressions equal to each other, what we conclude, because writing things out on a basis is unique, is that ci prime is equal to lambda I ci, like that. So in other words, ci of t is equal to ci of 0 e to the lambda I t. Right, that's calculus. Okay, so this is another motivator why we want eigenvectors of matrix, which is that if I know eigenvectors of my matrix, and I can write the initial conditions of my ODE in terms of them, then one thing I can convince myself is that I have a closed form solution for my ODE for all time. Right? So it's actually a perfectly reasonable way to solve an ODE, if you happen to know that it's linear, is to compute the eigenvectors of the matrix and then just use this formula here. Right? You kind of project everything into those eigenvectors. In fact, even what we'll see is that computing eigenvectors becomes more and more expensive the more eigenvectors you want. That's like not entirely surprising. So a very common approximation technique will be to just compute a few eigenvectors, project my initial conditions into that space, and hope that the action outside of that space isn't too big. Of course, when I say hope, there's an entire deep theory saying that that's like a reasonable thing to hope, but we don't know that yet. Actually, even we kind of do know that. Like, so for example, if lambda I is negative here, notice that like this term is going to decay really fast, right? And so you might just slice it out, which is like some indicator of which eigenvectors you want to choose. Okay. So anyway, that's our story for solving ODE with eigenvectors, which is a good first step. Similarly, I don't think we'll bother to do it in class because like enough already. Let's say that my matrix A has a complete set of eigenvectors. When I say complete, I mean they span Rn, right? So if I want to solve Ax equals b, if I write x, or rather I write b in terms of the eigenvectors of A, which I can do because they span Rn, one thing you can verify is that the solution x is a very simple closed form expression. You just divide every term by the corresponding eigenvector. Okay? This calculation is done in the book, but I think like enough already. It's a very similar calculation to this. Okay. As one more, slightly more involved application, let's talk about organizing a collection of photos or data points or whatever. So this is something called spectral embedding, which is a thing that you've probably, well, you may have encountered in machine learning class or Bayesian statistics class. This kind of idea shows up in a lot of different domains. And the basic idea is as follows. Let's say that I have a big database of photos. In this case, my photos are really boring. It's just a bunch of cars at different times of day. And now I'd like to take my photographs and lay them out on a line. It's actually a completely common thing you might want to do, right? So maybe one way that I could understand that would be I take my photos and I just assign a real number to these photos, right? So that's going to be kind of like my layout. And what I want is that things that are kind of in a similar position have similar photographs. So like, for instance, I want to organize from dark to light. Right? So this is starting to feel a little bit like that principal component problem already. You know? So there are so many different ways to describe this problem. Another one that people like that they call spectral embedding. If you take like a manifold learning class, this is the sort of first thing that you might learn, is that really what you've done is you've taken this high-dimensional database of photos and you're trying to project it onto the one-dimensional line here in a fashion that preserves relationships between the photos. That make sense? Notice that, by the way, these photos, like, they're not a bunch of data points that go through zero, so our PCA model doesn't quite work yet. Okay? So here's going to be our setup for this problem, which is suppose that we have n items in a data set. Okay? So for instance, just a collection of n photographs. And I'm going to have a value wij, which is the similarity of photos I and j. Okay? So w could be complicated, it could be simple, whatever. Like, for instance, maybe w is the difference in the average pixel value of the two things, or e to the minus that. Okay? But or I don't know, you use some deep network and it looks at the semantic content of your photo, whatever it is that I need to say to make you guys interested in this problem. Okay. And moreover, we're going to assume for now that we have a symmetry relationships, right? So the symmetry, the similarity between I and j is the same as similarity between j and I, which is this third expression here. Okay. Now our goal is going to be to essentially lay out these things on the real line. And what we want is that similar things are close. Right? That's going to be our goal. Okay? So how do we write this problem down? So first of all, actually, you guys tell me before I start flipping the slides around, like, what would be a reasonable, like, let's say that I'm your I don't know, your client. I lay out this problem for you. Now your job is to cook up an optimization objective function and a computational model. How would you do it? Take a stab. There's no wrong answers. Just answers I don't want. Well, so our unknown is a bunch of numbers xi. Yeah, so we have like probably, I'll give you this much. And again, we have a bunch of values j, and what do you want? We want that xi minus xj is small when wij is large. Yeah, because w is similarity, so it's big when we want them close, which is a thing we have to think through a million times. Okay? So here's one candidate, which is I sum over all my data points. I look at wij, and I just subtract. Right? So notice that this thing puts a big penalty anytime that xi and xj are far apart, but w is large. Does that make sense? I think this is a reasonable objective function, right? It's basically saying that like nearby stuff should somehow be similar. Yeah?
Kind of like it's a weighted least squares.
It is a weighted least squares. But it's a weird least squares in that what is the minimum of this problem? Thank you. You walked right into my trap. What is the smallest objective value? Yeah. Right? This thing just wants everything to be close, right? We all want to be close. That's great, but we can't all occupy the same space. Yeah? So we have this quadratic energy. It's actually secretly homogeneous because there's no linear term. Do you see that? Everything here is quadratic. So it's starting to look like the model that we're going to converge on again. Right, so far we have this thing. How could we make sure that everything can't be 0? It's like a pretty reasonable way to enforce that constraint. I mean, you guys know where I'm going because we've already seen like 4 examples of the same problem. Oh, wait. What was that? Sure. What's a good way, like how could I avoid all these things collapsing to 0? What could I add a constraint? Yeah.
Constraint to 1.
Yeah. I could do the following. Right? Because now clearly they can't all be 0 if these things square sum to 1, right? Am I done? Is my global optimum for this problem going to be interesting? Chris says no. How many of us agree with him? Relatively little support, I'm afraid. Yeah, most of the students think we're done. Or they're looking at their toes. Possibly both. All right, Chris, well, what's wrong? Yeah, so in particular, let's say that I have n of these things, yeah? And I take xi to equal 1 over the square root of n. Yeah? These numbers are not 0, so we actually did fix the first problem we were worried about. But they are all a constant. Do you see that? So that's not so good. So what can we do to avoid that problem? This is good. I mean, like, I think we should think critically about these models. I think it's so easy to just agree with them. Well, there's actually a lot of ways out of this problem. I mean, I hope you guys are thinking carefully. Here's a really simple one. One thing you might notice is that all of these things are positive, right? Like, I obviously could put a minus here, and that would also give you the same answer. But in particular, they're all on the same side of 0, right? One way to make sure that the xi's are interesting. Notice that this objective function does it change if I shift all the x's? No, right? Because it's always the difference between a pair. So maybe I just enforce that the average is equal to 0. If you're a fancy statistician type, you say you constrain to the first and second moments. Everybody see what I just did there? So I said the x's are basically mean 0 and variance 1. Yeah? And now we have an interesting problem. Now these things have to be different from one another. At least 2 of them. You see that? Fantastic. So now we're cooking with gas. This actually feels like a reasonable optimization problem. So we have 2 constraints. One of them says that we need, we don't want everything to be 0. The other says that they average to 0, which avoids this case where they're all constant and just not an interesting concept. Yeah. Okay. So, yeah, this is standard Gaussian in some sense. Yeah, at least for big I. Yeah. Okay. Actually, I'm sorry. I agreed to that too soon. It's not really the normal curve, but at least the first two moments agree with the normal distribution as mean 0 and variance 1. Yeah. Okay. So, what do you think we're going to do? We're going to show that this thing's an eigenvalue problem because it's the only thing that we're going to do in today's lecture, and obviously that's what we're after. Okay. So, in particular, when in doubt, I think the best thing to do is to just expand the square here. So our energy function E of x is equal to the sum over ij of wij xi minus xj squared, like that. We expand the square. We get that this is sum over ij j xi squared minus 2xi xj plus xj squared, like that. Notice that this is the sum xi, but there's a sum over j on the outside, right? So let's define a vector of value. So we're going to say that a is equal to w times the vector of all ones. So this is like the sum of the rows of w, right? By symmetry, by the way, a is also equal to w transpose times the sum here. Yeah. Yes.
All right, this is maybe like a step back.
Mm-hmm. That's okay.
Is this actually though the variance is one because you haven't subtracted out the second thing makes it the mean, but this is like the variance about.
Oh yeah. This is only the variance because we know that it's mean 0.
Yeah. Okay. So without that. Okay. Sorry.
Yeah, that's true. Okay. So this gives us a simpler expression, right? So this is of course we can think of it as 2 times the sum ai, xi squared. Do you see that? Because essentially the ai is accounting for the sum over j. Okay? Minus, and then we have this 2 times the sum over ij of wij xi xj, like that. Cool? Okay. So now we're basically business, right? So this, we can write this entire expression in a nice tidy way as 2 times x transpose a minus w x, where big A is equal to diagonal matrix of little a. This is just tidy notation for the same thing. You see that because this is already a quadratic form with w in it. Yeah. Okay. Any questions so far? I'm rushing through this only because I feel like we've done essentially the same calculation multiple times now. Like this is just expanding a square and then using tidy matrix notation to summarize it. Okay. So let's prove one useful fact, which is as follows. We actually can compute an eigenvector of this matrix. Let's see that. Any ideas, by the way? What's an eigenvector of? So we kind of know, like, eventually we're going to be aiming for eigenvectors of a minus w, right? That's clearly what we have in mind here. I claim you can just actually guess it pretty easily, which is the following: a minus w times the vector of all ones. What is this thing? Well, so remember that A is the diagonal matrix of little a values times vector of all ones minus w times vector of all ones. In general, when I have the vector of all ones and I multiply it by a diagonal matrix, what do I get? Yeah, I just get A. And A was actually defined to be the row sums of w. So this is 0. Yeah? So in particular, we showed that A minus w times 1 is equal to 0 times, right? So this is actually an eigenvector with eigenvalue 0, otherwise known as the null space vector. Yeah? So this is a useful fact. In fact, I noticed that in the book, for some reason, I do this second, and then I do the next thing first, and I actually think this is a little tidier. Okay. So here's going to be the claim, is that we still have an eigenvalue problem despite having these two constraints, And the reason we get so lucky is because of this fact here, that we happen to choose the second constraint that was an eigenvalue of our matrix. This is a very lucky circumstance, but actually a very common one, which is why I thought I'd show it to you. OK, this is actually the one case where that Eckert-Young theorem isn't needed because we just know that the first eigenvalue is irrelevant. OK, so what are we going to do? So if we return back to our original optimization problem, we now have a Lagrangian, which is as follows. Well, we know that it's equal to 2x transpose A minus W x, and now we have a lambda times 1 minus mod x squared. But now we need a second, what's the word I'm looking for? Lagrange multiplier, right, which is mu times the sum of the x's, which maybe we write like that. Cool? OK, so what are we going to do? We're going to differentiate with respect to x, because that's the only thing we know how to do. Yeah? So in particular, we get that 0 is equal to a minus w times x. Then we have, there's a 2 here. So we actually have a 4, right? You get a 2 from differentiating, and then there's the other 2 here. Then we have, here I'm not putting a 1/2, so you're going to get 2 lambda times x. And here, we're going to have mu times the vector of all ones. OK? Everybody with me so far? So here's a really sneaky trick. Let's pre-multiply by the vector of all ones. So in other words, I'm going to kind of pre-multiply by 1 transpose on both sides. OK? And why am I going to do that? Well, I'm going to get the following. I'll get 0 is equal to 4 times 1 a minus w x minus 2 lambda 1 transpose x minus mu. And then this is the dot product of the vector of all ones with itself, so that's just n if you think about it, right? Because it's 1 plus 1 plus 1 plus 1 plus 1. Cool? So first of all, what is this value? Zero, right? By the constraint. We know that x sums to 0. Thank you. OK. What is this value? Well, if I take this expression at the top of the board and I just transpose it, what I'm going to get is this expression. In fact, this is equal to 0 also. So what I'm left with is n times mu is equal to 0. N here is just some positive number. So in particular, we have concluded that mu is equal to 0. Sneaky, huh? OK. So if we return to this expression here, what we just learned is that really we have 4 times, in fact, we can divide both sides by 2, just for yucks. 2 times a minus w x is equal to lambda x. Notice that this is, like, we actually have included both of the constraints of our problem, but we still drew that this is an eigenvector. But we had to do a little bit of an argument to conclude that. Do you see that? OK. So fantastic. So we want n eigenvalue of this matrix. What is the last thing that we need to do? We have to figure out which eigenvalue. Right? There's a bunch of them. So in particular, if we return to our objective function, right, remember it's 2x transpose a minus wx. In fact, maybe I'll just continue over here so we can remember our expression, right? So we have 2x transpose a minus wx, but now we know that 2a minus wx is equal to lambda x. So we have 4x transpose lambda x, like that. The lambda is just a scalar, so we can pull it out. So this is really just for lambda. Yeah? Almost certainly the signs went wrong. Where did I make a mistake?
Your constraint has the expand now plus lambda numbers that change to minus.
Oh, did I? Sorry. Oh, yeah, you're right. I'm sorry. Fine, so let's just do like that. This is actually disagreeing with the book and with my notes, but I believe it's still correct. As usual, I've made stupid mistakes. Sorry, this is... Well, they say that this is why you teach this class first with these temporary course numbers, but the reality is that like I'll teach something 9 times and make the same mistake every time. Yeah, but in any event, notice that, of course, x squared minus 1 is equal to 0, 1 minus x squared is equal to 0, so either one is actually fine in the Lagrangian. But I will a posteriori put that there so that I don't have to fix a bunch of other plus signs. OK, thanks for catching that. I do imagine that this is going to make the book's definition of lambda and mine opposite sign from one another. So do be careful about that when you read the course notes. OK. But we'll continue reading through. I might as well put my notes down. OK, so we have 4 lambda. So in particular, what do? We compute all the eigenvectors of A minus lambda. And what is our embedding x? X is an eigenvector of 2A minus W, or A minus W, doesn't really matter. And remember here, we minimize, right? So we want to minimize the objective value, which is 4 lambda, right? So in particular, we want with smallest lambda. Is that quite right, though? Let's say that A minus W is positive definite. Then there's one case I have to be a little careful about. Well, if it could be that the smallest eigenvalue of this thing is 0. In that case, what do we know? That it's the second smallest eigenvalue. Right? So in particular, we want the smallest eigenvalue that's non-zero. Right? Because essentially the way to remember that from our argument here is what we've shown here, right, is that, From this expression here, we've shown that despite the fact we had the second constraint, x is still an eigenvalue of words are hard today. I'm sorry. I'm tired and distracted. The math on the board here has shown that x is an eigenvector of A minus W, right? And we did that carefully. Like we accounted for the constraint when we did that. And we showed that even though we had that constraint, we still got an eigenvector. The question is which eigenvector? And so what we did is we went back to our objective function. We said, OK, we could plug each of our eigenvectors into this expression. And then obviously, we should choose the one that makes that the smallest, right? And essentially, when we do that, we get is that the value we're going to get is 4 lambda, right? So we want the one with the smallest lambda, except if that lambda is 0, then we ran into trouble. So then we choose the next smallest one, right? OK. So there's our argument. That makes sense? Any questions? So we started with this kind of funny little embedding problem, and we ended up with just another eigenvalue problem. And by the way, like that's precisely what happens. Like if you look at these spectral embedding things, this is all they are. They're coded in fancy language, but this is it. Incidentally, if you take my fancy grad level course, you will spend about, I would say, 1/3 of the course analyzing this matrix and variants thereof. Does anybody know what this thing is called? This object is called the graph Laplacian. So in particular, essentially what you're doing is you're sort of comparing elements of x to their neighbors, right? Like that's, if you think about it, this is kind of like a weighted average of the neighbors of x minus x, right? The other way around. Which if you think about the Laplace operator, like the second derivative, also kind of looks like that. You're like comparing points to other nearby points. And so like heat diffusion, spectral theory, all kinds of beautiful things come out of this. In fact, the way that I usually motivate a lot of partial differential equation, which we will not see in this course, is to start with the graph theory case, which is very concrete and tangible and looks like a nice eigenvalue problem we know how to deal with, and then kind of take a nice limit and show, like the smooth version is very similar. Okay. But that's tomorrow problem. And by tomorrow, I mean like 3 semesters from now. Okay, so that's what we've shown so far. So in any event, hopefully I have convinced you all that there's a very useful object associated to a matrix, which is called an eigenvector. And an eigenvector is a non-zero vector that satisfies AX equals lambda x for some lambda. And lambda is an eigenvalue. Notice that I've sneakily included the complex numbers here. Right? We're going to have to justify when we have eigenvalues that are only real value. But for now, we'll allow them to be real or complex. Okay? And of course, the relationship AX equals lambda x scales with x. So it's perfectly fine to scale the norm of x up and down. Okay? A few more definitions, and then I think we'll call it for today, mostly because I could use a bathroom break. We're going to define a particular object called the spectrum of a matrix, which is the set of all eigenvalues of this thing. By the way, oftentimes we think of the spectrum of a square matrix, an n by n square matrix, as having size n. And often that is the case, but not always. So when you have a full matrix, or a full set of eigenvalues, that's a good thing. And otherwise, we call your matrix defective, which is a little bit sad. But lots of defective matrices show up in real life, and they're legitimate too. Okay? And the spectral radius of a matrix is the biggest eigenvalue of the matrix. You might remember what was the 2 norm of a matrix? It kind of looks like that. So a spectral radius is just like a very close to how you compute the norm of a matrix. Okay? And of course, what we've essentially seen at the beginning of the lecture here, there's so many eigenvalue problems in the wild. I mean, there's like minimize the norm of a vector subject to length 1, assorted ODE, PDE problems. A third one that we didn't see is critical points of a ratio of 2 quadratic functions. Notice that this is basically the same as the first problem, right? Because you're like normalizing by the norm of x here. So all of these things lead to the same eigenvalue problem. Sound good? Okay. So I think maybe what we'll do, because this class has a tendency to get ahead, I'm going to allow myself to fall behind a tiny bit. So starting the next lecture, we're going to prove a couple properties of eigenvalues that are going to be useful. I mean, I'm assuming essentially in this class that you've seen an eigenvalue, but you don't remember anything about it, which I think is a typical assumption among computer science students. So we're going to spend a little bit of time convincing ourselves that such an object should exist, right? We haven't actually done that. In particular, all matrices have at least one eigenvalue. And then we will motivate, we're not going to prove because we don't know enough about compactness to do that in this class, that symmetric matrices have a full set of eigenvalues, namely n of them, and their eigenvectors span Rn. Right? This is called the spectral theorem. So we'll do that in the first half of our next lecture, and then we will derive many, many algorithms for computing eigenvectors. By the way, you could take an entire course on computing eigenvectors very easily. This is a giant problem in the world of computational science. But we're going to motivate some of the basic ones, which actually all have very similar flavor. And they're also, in some sense, the world's most boring algorithm. I mean, essentially what we're going to do is take a vector and multiply it by by a bunch of times. And then maybe do a little accoutrement around the outside to clean it up. Okay? So with that, maybe we'll call it for the day. I'm sorry, I need a break to have major calls. But with that, we'll continue next time. In the meantime, make sure that your homework runs, again, on your computer. I'm going to keep reminding you of this because I don't want to debug at the last minute. I really don't. And with that, I will see you on Tuesday.